Hi, I'm Yamireki, co-founder at Statecraft Laboratories, and today we'll explore an exciting and innovative authentication system that we have developed, the Coconuts and Oblivious Computations for Orthogonal Authentication Protocol, or simply the COCO. COCO is a privacy-first protocol designed to authenticate users without requiring knowledge of their identity or the reason for authentication. It eliminates the need for both the user's username and secrets during authentication while ensuring secure and reliable access control. Before delving into the protocol, let us introduce the key entities involved. Authenticators are independent authentication servers that verify client credentials. Multiple authenticators can be added, depending on the security requirements. Verifier is the tenant's service or application which has a modified workflow to support COCO. Clients are users attempting to register or gain access to an account, and the global database is a central repository that stores verification keys, enabling authenticators and verifiers to retrieve these keys. It is important to note that the authenticators are specific to each verifier. An authenticator for one verifier cannot be used by another. Let us now walk through the steps of the registration process. While it may seem complex initially, we will break it down step by step, starting from generating the user IDs. First, the client takes the username, blinds it, and sends the blinded username to the verifier. The verifier performs an OPRF evaluation on the blinded username and sends back the blinded evaluation to the client. At this point, the client unblinds the OPRF evaluation to obtain the user ID. Note that the verifier still does not know the username or user ID at this stage. Moving on, the client takes the user ID and generates a time-bound blind signature request using the Coconut credential scheme, with the username as the blinded subject and the scope set to access registration. It then sends the user ID and the blind signature request to the verifier. The verifier checks the user ID in its local database. If the user ID is available, the verifier blind signs the registration access request and sends the blind registration token along with the verification key for the blind registration token and the verifier white common pepper back to the client. The verifier also sends the verification key for the blind registration token to the global database for storage and later retrieval by the authenticators for registration finalization. Now, the client generates as many random solves as the number of authenticators it plans to use with COCO. It then creates self-signing keys for each authenticator. Each key is a hash of the user ID combined with the pepper and the hash of the user's password combined with the authenticator's specific salt. Next up, we proceed to generating authentication identities. The client generates a time-bound blind signature request with the scope set to evaluate OPRF and sends it separately to each authenticator. Each authenticator verifies the time binding and a scope, blind signs the OPRF access token, and sends back the blind OPRF access token along with its verification key to the client. The verification key is also sent to the global database so that it is visible to other authenticators. The client aggregates all blind OPRF access tokens into a single access token. The client then blinds its self-signing keys separately and sends them along with the proof of aggregated OPRF access token and all verification keys to each authenticator. Each authenticator retrieves the verification key for the OPRF access token from the global database, verifies its validity, and performs the OPRF evaluation on its respective blind self-signing key if valid. It then returns the blinded response to the client. The client unblinds the OPRF responses from all authenticators and generates separate authentication identities for each authenticator by hashing the respective self-signing key with the authenticator's salt and concatenating all the authenticators' OPRF responses. The final step is about creating self-signatures and asking the authenticators to store their respective verification keys. Hence, the client self-blind signs the authentication identities using the respective self-signing keys. It then sends the authentication identities, self-blind signature proof, verification key for the self-signature, blind registration token, verification key for the blind registration token, and a blind signature request for presenting as proof of authentication separately to each authenticator. Each authenticator retrieves the verification key for the blind registration token from the global database and validates the registration access token. Upon successful validation, the authenticator verifies the proof of the client's self-blind signature and stores the verification key along with the authentication identity in its local database for consequent authentications. The authenticator blind signs the access token for presenting as proof of authentication and sends it, along with the verification key, to the client. It also sends the verification key to the global database for the verifier to retrieve. The client aggregates all blind access tokens for presenting as proof of authentication into a single login access token. It then goes on to send the proof of this token along with all verification keys, the user ID, and the sols to the verifier. The verifier retrieves all verification keys from the global database and verifies the proof sent by the client. Upon successful verification, the verifier stores the sols along with the user ID in its local database. Let us now walk through the steps of the login process. First up, fetching stored variables for creating the self-signing keys and authentication identities, the client blinds the username and sends it to the verifier. The verifier performs an OPRF evaluation on the blinded username and sends back the blinded evaluation to the client. The client unblinds the evaluation to obtain its user ID. The client then sends the user ID to the verifier in exchange for the associated sols and pepper. Now, once the client has obtained the required variables, it goes on to recompute the authenticator-specific self-signing keys and the authenticator-specific authentication identities. Finally, the client self-blind signs the authentication identities using the respective self-signing keys and sends them, along with a proof of self-blind signature and a blind signature request for presenting as proof of authentication to each authenticator. Each authenticator verifies the proof of self-blind signature using their stored verification key. It then blind signs the access token for presenting as proof of authentication and sends it along with the verification key to the client. The verification key is also sent to the global database. The client aggregates all blind access tokens into a single login access token and sends it along with all verification keys and the user ID to the verifier. The verifier retrieves the verification keys from the global database and verifies the proof sent by the client. If valid, it confirms that the client has authenticated with all the required authenticators. The verifier can now grant access to its resource. Currently, our COCO protocol has a support for the following features. It supports user registration, login, credential login, second factor authentications, deletion, username or public handle updates, and secrets and password updates.